All right, it is it is 2025, and it is November 20th, approximately, see this, 2:45 a.m., and we're continuing with 7.1, which is basic definitions and examples of rings, well, everything that we cover in Chapter 7. Not just rings, of course. But for the most part, it's mainly ring theory. But anyway, let me get this arranged. Oh, I've got to set this. Forget that. Okay, so when we left off, we were talking about integral domains, and we left off with a final corollary, that being that any finite integral domain is a field. Now we move on to some assertions that the book here makes before getting into some examples. So here's an assertion that the book makes. Is this thing on? Yeah, it's on. Okay. It's yeah. Oh, wrong writing utensil. There we go. So there's this interesting result, which is that a finite division ring is necessarily commutative. And furthermore, well, that is a field. And this is attributed to Wedderburn. And it says that there's more to be said on it whenever we get to section 13.6, which will be way later, but that's the assertion that that's an assertion that the book makes. And then another more concrete assertion, at least insofar as our current section is concerned, is that every non-zero element of a commutative ring that is not a zero divisor has a multiplicative inverse in some larger ring. Which now gives a book here notes that this gives another perspective on the cancellation law in a proposition that we covered earlier. So that's a nice thing to point out right there. Before we get into another definition. So, having defined the notion of a ring, there's a natural notion of a subring. And this, of course, is, well, a subring of the ring R is a subgroup of R that is closed under multiplication. So in other words, a subset S of a ring R is a subring if the operations of addition and multiplication in R, when restricted to S, give S the structure of a ring. Now, to show that a subset of a ring R is a subring, it suffices to check that it is non-empty and closed under subtraction and under multiplication. So that's worth writing down, I think. So to show that a subset of a ring R is a subring, it suffices to check that it is non-empty and closed under subtraction and multiplication. All right, so let's move on to some examples. I'm hoping that I have enough storage on this. I need to get like a dedicated thing for recording, but as it stands, I'm just using the same device as I use for everything else, which is just my iPhone. But we'll see. Okay, so some examples. Well, here's an example. So the integers is a subring of the rationals, and the rationals feels weird saying is, but the set of the rationals, I guess you could say, is, because you'd say the rationals are, but it's just that the entire thing is one thing. So there's a subring of the real numbers. So what we have here is that the property is a subring of is clearly transitive. All right, so that's a nice example. So let's move on to another one. So two integers, even integers, is a subring of the integers. As is any sort of multiplication by the integers here for any integer n. So, yeah, that's pretty cool. But here's the thing. The ring integers mod n is not a subring or a subgroup for that matter of the integers for any n greater than or equal to 2. All right? Here's another example. So, the ring of all continuous functions from the reals to the reals is a subring of the ring of all functions from the reals to the reals. Now, the ring of all differentiable functions from the reals to the reals is a subring of both of these. So it's interesting how that works in a way, because just the nature of how continuous functions relate to differentiable ones. I mean, going back to calculus again, it's like this is just blew my nose there. There's no elephant here except for me, but just giving a different language to this relationship in between continuous and differentiable is nice to see. But yes, okay. Now let's move on to another example. And that is the integral. Oh, I'm not going to say too much here, except because then I'd have to go into this long monologue about it. But so say we have s is equal to the integers plus the integers I plus the integers j plus the integers k. So this, the integral quaternions form a subring of either the real or the rational quaternions. Now the book here notes that it's easy to check, supposedly easy to check that multiplying two such quaternions together gives another quaternion with integer coefficients. Now this ring, it further notes here that this ring, which is not a division ring, can be used to give proofs for a number of results in number theory. So obviously it's very important to the number theorists, or at least was at some point. Well, is because it's historically important, I guess. Without which none of this could happen. So here we are. Now let's move on to another example. So if R is a subring, camera's good, of a field F that contains the identity of F, then R is an integral domain. Integral domain is an integral domain. So if R is a subring of a field F that contains the identity of F, then R is an integral domain. Now, the converse of this is also true. So any, oh, that should be a colon, not a semicolon. Any integral domain is contained in a field. Okay, again, that's how it is. All right, now let's move on to, well, this is going to be a bigger example because the book gives like a whole big bold section here on this particular example, which is going to be titled here. Give me a moment. I'm gonna scratch my back. Yeah, okay. All right, so this example is titled, so this example gets a big bold print, and it gets a title, a parenthetical title, which is quadratic integer rings. So let's let D be a square-free integer. So from the addition and multiplication that the subset of the integers okay, I'll just say this. From addition and multiplication, the subset and this is going to be weird notation, so I'll just say it outright. Integers, open bracket, square root of capital D, close bracket, is equal to the set containing A plus B, square root of capital D, such that A and B are integers, forms a subring of the quadratic field. So now if d is equal to 1 mod 4, then the larger subset, in the book here notes slightly larger subset of the integers, here in this case bracketed 1 over square root of capital D over 2, is equal to the set containing a plus b times open parentheses 1 plus square root of capital D over 2, such that a and b are integers, is also a subring. So we're just sort of collecting subrings from the quadratic, the quadratic field, a quadratic field. I'll say the quadratic field for purposes of this discussion at this moment, is also a subring. And we could just show this real quickly by saying, okay, by looking at this. Closure of addition is kind of immediate, but the book makes specific efforts to show this little number here times this little number here is in fact going to result in the closure of multiplication. So I'm going to say all that right now just to have it written down. So yes, open parentheses, a plus b times 1 plus the square root of capital D over 2, close parentheses, open parentheses, c plus d times 1 plus square root of capital D over 2. That's equal to open parentheses, ac plus bd times d minus 1 over 4, big D minus 1 over 4, close parentheses, plus ad plus bc plus bd, close parentheses, times 1 plus square root of capital D over 2. So together with the congruence on D shows closure onto multiplication. On capital D shows. All right. Now, from this, we can extend into defining something else, which is this, uses this O notation that we used for orbits earlier, but so how would I say this notationally, literally? So I can't remember what this is. I really should have like a chart of Greek letters just so that I can just look at it and then say, but I'll just call this big O for now. I know that's an abuse of like everything here. But let's just say, okay, you can, whenever I say big O, just replace it with what it actually is. So big O is equal to big O sub the quadratic field, which is equal to the integers open bracket omega close bracket, which is equal to the set containing a plus b little omega a b within the integers. So, and this is where little omega here is equal to the square root of capital D if D is congruent to 2 or 3 mod 4, and equal to 1 plus the square root of D over 2 if D is congruent to 1 mod 4. Now, this is called the ring of integers. The ring of integers in the quadratic field and the terminology comes from this comes from the fact that the elements of the subring big O of the field of the quadratic field have many properties analogous to those subring of integers in the field of rational numbers, and are the integral closure of the integers in the quadratic field. So that's a neat little example there. Quadratic integer rings, the ring of integers in the quadratic field. So from that, the book then goes to describe, definitions, more definitions, but in this case, those they're not like official definitions. They're not like things that get their own little bold thing. They get like italics, but let me just go ahead and write this down. So, in the special case, when d is equal to -1, we get z open bracket close open bracket little I close bracket of Gaussian integers, which I've seen before, and I'm sure a lot of you have seen multiple times, but because they're pretty important. And these are the complex numbers a plus bi contained within the complex numbers, with a and b both being integers. So these numbers were originally introduced by Gauss around 1800 in order to state the biquadratic reciprocity law, which deals with the beautiful with what the book notes as the beautiful relations that exist among fourth powers modulo primes. Now, we'll see another useful application of algebraic structure of this ring to number theoretic questions. So, particularly, the book here notes field norm n, such that we have this map from the quadratic field to the rationals, defined by n open parentheses a plus b square root of capital D close parentheses is equal to open parentheses a plus b square root of capital D close parentheses open parentheses a minus b square root of capital D close parentheses is actually equal to a squared minus b squared, which this is contained within the rationals. And this is non-zero. It's non-zero if a plus b square root of capital D is not equal to 0. Now, this norm gives a measure of the size in the quadratic field. So, for instance, when d is equal to -1, the norm of a plus b I is a squared plus b squared, which is the square of the length of this complex number considered as a vector in the complex plane. Now, the book will use the field norm in this and subsequent examples to establish the many properties of the rings that we discussed earlier. This example, the quadratic integer rings, right? So that's important to note there. And the book goes on to make more assertions on this fact. So the norm is multiplicative So we have some, let me bracket that. Well, actually, you know what? Let's do this. So the norm of some alpha beta is equal to the norm of alpha norm of beta for all alpha and beta contained within the quadratic field. Now on the subring of the quadratic integers of the quadratic, let me say this. Yeah, on the subring of the quadratic integer rings. So, which I'll just say is big O for now, because that's easier to say. On the subring, big O, we have that the field norm is given by field norm is given by n of a plus b omega, which is equal to open parentheses a plus b omega, close parentheses, open parentheses, a plus b omega bar. So this residue class looking thing is equal to a squared minus capital D b squared if capital D is congruent to 2, 3 mod 4, and it's equal to a squared plus ab plus 1 minus d over 4 b squared if d is equal to, well, as d is congruent to 1 mod 4. And this is where, so actually the omega bar is defined differently here, not in terms of really residue class explicitly, more so just omega bar is equal to negative square root of capital D if D is congruent to 2, 3 mod 4, and 1 minus the square root of capital D over 2 if D is congruent to 1 mod 4. Now, it follows from this that the norm is in fact, the norm of alpha is in fact an integer for every alpha contained within big O here. So the book then goes on to make more assertions here in this very long example, but it's a good example, I'd say. If you can draw a whole bunch of little examples from an example, then I'd say that makes that a good example. Now, the quadratic integer ring, we may use this norm to characterize the units in big O. Now, if alpha of big O has field norm n of alpha to be equal to plus or minus 1, then the previous formula shows us that open parentheses a plus b omega close parentheses to the negative 1, the inverse of a plus b omega is equal to plus or minus open parentheses a plus b omega bar, which is again an element of big O here, and so alpha is a unit in big O. Now, suppose conversely, alpha is a unit in big O. Say alpha beta is equal to 1 for some beta in big O, well, then the multiplicative property of the field norm, it implies that n of alpha, n of beta, is equal to n of alpha beta, which is equal to n of 1, which is equal to 1. Now, since both n of alpha and n of beta are integers, each must be plus or negative 1. So the element alpha is a unit in big O if and only if the norm of alpha is equal to plus or negative 1. Now, book here says that in particular the determination of integer solutions to the equation x squared minus capital D y squared is equal to plus or minus 1, called Pell's equation in elementary number theory, is essentially equivalent to the determination of the units in the ring big O. So, kind of wish I had more number theory in my background for this. Then I could see that, have like a little bit, but only like a undergraduate sort of knowledge of the subject. Okay, so then the book makes some final assertions here. So in this section, so when D is equal to negative 1, the Gaussian integers are the elements a plus bi with a squared plus b squared equal to plus or minus 1, with a and b being integers. So further, the group of units here consists of the set plus or minus 1 and plus or minus I. Now, when D is equal to negative 3, we have that the units in the integers, in the Gaussian integers define this, well, the integers define this part with the bracketed open parentheses 1 plus the square root of negative 3 close parentheses over 2 close bracket are determined by integers a or b with a and b with a squared plus AB plus B squared equal to plus or minus 1. That is to say, with open parentheses 2A plus B close parentheses squared plus 3B squared is equal to plus or minus 4, from which it's supposedly easy to see that the group of units here is a group of order 6 given by plus or minus 1 plus or minus p plus or minus p squared, where p is equal to, or that could be rho, could say that's rho, is equal to square, open parentheses, -1 plus the square root of -3, close parentheses, over 2. And what's interesting is that for any, so whenever d is greater than 0, it can be shown that the group of units for big O here, so the group of units big O to the x is always finite. Is always infinite. It's the exact opposite. It's always infinite. And the book lists a particular example here. 1 plus the square root of 2 is a unit in the ring big O, which is equal to the integers bracketed square root of 2 with field norm 1. And that the set containing plus or minus open parentheses 1 plus the square root of 2 close parentheses power n such that n is an integer is an infinite set of distinct units and in fact the full group of units in this case so that's essentially, so all of that is essentially what's mentioned in section 7.1, the basic definitions of examples and examples for the start to the introduction of rings. And that is it for now.